Hello and welcome to Calculus 2 here at Cañada College. My name is Lapuz. In this video we'll be looking at checkpoint 6.12 from section 6.3. It says to find the first and second Taylor polynomials for this function f of x is equal to square root of x at x is equal to 4. And after that we want to use these polynomials to estimate the square root of 6 and then to use Taylor's theorem to bound the error. Here's Taylor's theorem with a remainder that says that the remainder is, well, naturally be equal to f of x minus p sub n of x. But just to get a boundary for this, r sub n of x, that's the remainder, is going to be less than some sort of maximum value for the n plus first derivative divided by n factorial times x minus a to the n power. Alright, so we got some bounding going on, and let's start with the simple parts. Let's find the Taylor polynomials first, the first order and second order Taylor polynomials, and then we'll plug in the 6 for that. Okay, so just off to the side here, we would want to figure out what the derivatives are. Well, first of all, f of 4 is going to be equal to the square root of 4, which is equal to 2. So that part's okay. We need a couple of derivatives. We're going to take this derivative, so I probably would like to write this first as x to the 1/2 power to make things a little bit easier. So f prime of x will equal to 1/2 x to the negative 1/2 power. That's 1 over 2 square root of x. That'll help me evaluate that in a minute. The second derivative will be a negative 1 over 4 x to the negative 3/2 power. So this is negative 1 over 4 times x to the 3/2 in the denominator. And so let's take this for now and put in the value of 4. So f prime of 4, that would be 4, is equal to 1 over 2 times root 4. Root 4 is 2, so 1 over 2 times 2 is 1 over 4. F double prime of 4 will be equal to negative 1 over 4 times, this is going to be 4 to the 3/2 power. 4 to the 1/2 is 2. 2 times 2 times 2 is 8. 8 times 4 is 32. So negative 1 over 32. Okay, so we got our results. The first Taylor polynomial, second Taylor polynomial will come up looking like this: p sub 1 of x. This is the first polynomial. Is going to be f of 4, so that's 2, plus the derivative, so that's 1/4, and then x minus, and then remember the 4 is the center point. So this is our first polynomial. Our second polynomial, p sub 2, is going to be the same thing, 2 plus 1/4 x minus 4, and then now we have to add on a negative 1 over 32. Oops, we have to also divide that by 2 factorial, and then x minus 4 to the second power. 2 factorial is 2, so I think this will end up to be 1 over 64. So let's rewrite this whole thing. This is 2 plus 1/4 x minus 4. I believe this is also a negative, so let's not forget the negative sign there, and I did forget. And this is a 32, not 3 squared. 32. So instead of a minus here, or instead of a plus that I was going to write, this should be a negative 1 over 64 x minus 4 squared. Okay, so here's our P1 and P2. So that's the first part. The second part is to, they say, use the polynomial to estimate 6. So to estimate the square root of 6, we're going to use this polynomial and evaluate this at 6. So this is going to be 2 plus 1/4, 6 minus 4, where we put in the x. So this is just 2. This is going to be 2 plus 1/4 times 2. I believe that is a 1/2. 2 plus 1/2 is 5/2. I suppose we want to put that into the calculator and get 2.5. Alright, we'll do the same thing here. The square root of 6 is going to be approximately equal to our second polynomial evaluated at 6. So we have 2 plus 1/4 times 6 minus 4, which we already computed here, right? This whole thing is equal to 2.5. And then we'll add on 1 over 64, and then x minus, or x is equal to 6. So this is going to be 6 minus 4 squared. So this is 2 squared. 2 squared is 4. 4 into 64 is going to be 1 over, so that's going to be 1/24, 16. This is going to be 1 over 16. And I think if we put all that into the calculator, this will give us 2.437. Alright, so we got 2.5 for the first estimate, 2.437 for the second estimate. We do have calculators to figure out what the square root of 6 is, but let's keep going with this idea of looking for the boundary. So let's imagine that we're going way back before we had calculators, and we were now trying to figure out how much of an error are we getting here. So to figure out the error for the first polynomial, this is our first polynomial, the error for our first polynomial, we need to go to the second derivative, and then we're going to evaluate it at some value that would give us the maximum. And this is going to be within some interval between x and a. So our x is equal to the number that we're putting in, 6, and our a is equal to our center point, which is equal to 4. Okay, so in other words, what we want to do is we want to take a look at our second derivative. Let's do this first one first. To figure out the error term, we need to find our second derivative. So let's rewrite that. F double prime of x is equal to, let's just see what we got here, negative 1 over 4 x to the 3/2 power. So negative 1 over 4 times x to the 3/2 power. And then we want to see what that is for the interval. Let's go from the interval of x. This is the x value that we're putting in, and that's 6. And then this is the a value that we have is 4. So within here, what is the largest value? So x to the 3/2 is an increasing function, and as it goes up, so this is going to be some sort of power function that goes up, increasing. So this will give you the largest value when x is equal to 6, or the value is equal to 6. But this is a negative here, which means that this 4 is going to give you the largest value. So in the theorem, they want us to find the maximum number. There exists a real number m such that this is going to be, m is going to be the largest of all those values. So let's find capital M here. capital M is going to be max value within this thing. Actually, if we're also interested in taking the absolute value of that. So if we take the absolute value of that, so it's going to be 1 over 4, and then we're going to have x to the 3/2 power. If we put 4 in there, we're going to get, let's say, the absolute value of this, so ignore the negative sign. If we put 4 in there, we're going to get what we got. So we're going to get 1 over 64, I think is what we said. No, 1 over 32. And then if we put 6 in there, we're going to get 1 over some number that is going to be larger than 32. So a number bigger than 32. So it's bigger in the denominator. Oops. Bigger in the denominator, so then the whole fraction is going to be less than that. So this number is going to be less than this, which means this is going to be the larger value, and that larger value happens here. So I would say the m, the maximum value, should equal to 1 over 32. Okay, so now we'll put that in here to get our boundary for the remainder. And remember, this is all working with n is equal to 1. So n is equal to 1 here, just to be clear. This is the side where we did the first polynomial. And according to our theorem, r sub 1, let's get that theorem straight here. R sub 1 of x, the absolute value of that, absolute value of r sub 1 of x is going to be less than m divided by 1 plus 1, n plus 1 factorial. Let's just write the formula down, since we're just writing the formula down anyways. And then we have x minus a to the n plus first power, I believe. Yep, n plus first power. All right, so when n is equal to 1, and then we're going to put 6 in. So r sub 1 of 6 is what we really want. This is going to be bounded by 1 over 32 divided by 2 factorial times, this is going to be 6 minus 4 to the second power, because n is equal to 1. All right, what do we get? We're going to get 1 over 64, what we got before, and then this is going to be 2 squared, which we did this already, right? We got 1 over 16. That's kind of like the remainder. So this is going to be 1 over 16. And what's 1 over 16? 1 over 16 is 0.0625. 0.0625, and this is going to be your remainder. Okay. All right. So that is our remainder analysis for our first polynomial, and you can see it is essentially this second part over here where you put 6 in. So we didn't do it for the third one because we'll need the third derivative, but we'll see the same analysis happen. All right, this is our second derivative. Here we need our third derivative, so to get our remainder for the second polynomial. So let's take our derivative the third time. So this is going to be 3/2 times 1/4, negative, negative, so that's going to be a positive 3 over 8 x to the minus, and then we'll subtract 1/2 again, or subtract 1, so that will give us negative 5/2. All right, this is our scenario once again, and we're trying to find the maximum value here between 4 and 6 is our interval. And again, this is like strictly increasing or decreasing function. So in finding the absolute value of what's happening here, 3 over 8 x to the 5 halves power. Let us put in the value of 4 and 6 to see which one's going to be larger. These are negative. This is a negative power, so this goes down in the denominator. And it looks like it's going to be the same story. We got 3 over 8 and then 1 over x to the 5 halves power. So if we put 4, we're going to get a smaller number in the denominator than if we put 6. But a smaller number in the denominator will make this bigger than when you put 6 in there. So put 4 in there, 3 over 8, and put 6 in here. And this is going to be greater. So we're going to pick this number again, and that's this number over here, which, by the way, we need to figure out what 4 to the 5 halves is. So 4 to the 1 half is 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 4 times 2 is 32. So this is 32 times 8. And 3 divided by, and then 32 times 8 is going to be 32, 16, 20, 256. Okay. So this is our m value that we will use for our boundary. And so r sub, this is our formula, so I'm not going to write it again, but we know that this is going to be the remainder for our second polynomial, r2 of x. I'm just going to put 6 right away because, again, we know the formula already. And that is going to be bounded by 3 over 256 divided by 3 factorial, which is going to be 6, and then we're going to multiply it by 6 minus 4 to the third power. Okay. All right. After some analysis of this, I believe this will turn out to be equal to 0.015625. Okay, so that's going to be your remainder for 6. You see that the remainder is a lot smaller than the first time, and this is 2.5, this is 2.43, and just to let you know, if I actually put the square root of 6 into the calculator, square root of 6, this is approximately equal to 2.449487, and I'll just put ... here. But that's the actual value. So if you were to think about adding 2.437 and add it to 0.0156, you should get something that's very, very close to this. Okay. All right, that was a long one. I hope that helps. And just to summarize, we have our Taylor polynomials here for the first and second polynomials. We have our approximations here for the square root of 6 approximations, and then we found our remainder terms. Okay, hope that helps. Good luck.